Daughtry. Andy's here. All right. This is Gore, Caffrey, Kohler. There's McCaffrey.
Mr. Gaffney, people are saying to tell you to let them in.
Yeah, well, I'm letting them in as they sign up.
Oh,
Mr. McCaffrey, can you hear me?
Yeah.
In the Dropbox, I think you got a couple classes mixed up for that problem set one from Monday. You put in there, like maybe it was a physics or a bio
Oh, shit.
problem set that was in there. So
All right.
that teacher may have the stats problem set, and I've got the other one. Okay,
Word.
I gotten crisscrossed. Let me just do my quick roll here, and then we'll get the ball rolling. Let's see. Or missing Walden. Is Walden out there? Don't see him. Tollers, don't see him. Gore is here. Okay, I think we got enough to get the ball rolling. Make sure the thing's recording. All right, welcome. Wednesday, April 22nd, stats. I hope everybody's surviving. Maybe getting outside a little bit, enjoying some of the nice weather. Let me just kind of give you the lineup for today. I don't have any new announcements from what we went over on Monday. So what we're going to do today is all but like 3 or 4 of you, maybe 3 of you sent me your 6-5 problem set from the other day. So I printed them out this morning, scored them, put them in Blackbot. I'm going to talk about that briefly.
got mine?
Got yours, Mr. Daughtry?
Here's mine.
Mr. Halls, Mr. McCaffrey, I think I got his biology or physics paper.
Did you get mine?
Mr. Gore, I got yours. I did not get Mr. Tomlin's and Mr. Walden's.
Here's
A little leak.
Okay, let me hold it real still. I'm looking. Okay. I got yours, Mr. Hall.
Freaky leak.
Okay, and so I'm going to kind of talk about that, a couple little errors, some problems on a couple of them that were a little bit common. We'll get that problem worked out. And now today, it's already in Blackbot. There's a problem set number 2 on 6-5, which we're now going to do some applications of this normal approximation of the binomial, which I'm going to do a quick recap on. And I think there's 5 or 6 problems on there. There's 5, one of them has the A and B parts. There's actually 6. And I'm gonna walk you through number 1. I'm gonna maybe get you started on number 2. And then I'm gonna give you a couple watch out for us, make sure of zone 3 and 4. And then I'm gonna let you finish those up. And if you would put those in Dropbox by Friday afternoon, that would be great. I'm gonna back up the calendar I proposed a couple days ago a little bit. We're going to, because I said I was going to do a chapter 6 test like after today, but I don't think we're quite ready there because I want you to kind of master this normal approximation. And I don't want to give you a test on some material I haven't quizzed you on. So I think what we'll do is we'll quiz on this last half of chapter 6 on Monday, and I'll give you the test after Wednesday's class. I think it's a little fairer, a little more practical, and you'll be a little better prepped. I want you to be prepped for the test because that'll probably be the one and only test on this quarter's screening test. So I don't want to set you up for an effort and frustration if you do. So that's kind of the plan. All right, any questions before we jump into it? All right, so here we go. The normal approximation of the binomial, okay? And just to kind of recap and review, why are we doing this? And what is it? It sounds pretty impressive, but what exactly is it? And remember the binomial is we started binomials clear back about midway through third quarter with that 4-question top quiz that you had to answer the questions for, that there were no questions for, and guess. And we did those, we did all the calculations. What's the probability of getting 1 correct answer or no correct answers or 2 correct, 3 and 4? That's a binomial, all right? It's a statistical scenario where it's structured in a fashion that there's only 2 outcomes: success, failure, right, wrong, yes, no, black, right, Democrat, not Democrat, senior, not senior. There's only, it's structured in a manner that there's only 2, and that's why there's only 2 possible outcomes. And it's very common and easy to do, all right? And if you remember the calculations, we had that little binomial coefficient with the n over x, and we had that factorial stuff, which told you how many different times that the probability of getting 2 correct answers out of a number of 4 trials. And I think we had like a 16 branch flow chart to kind of demonstrate that. And we talked about once you get above 4 trials, the flow chart is logistically not even practical. And you remember, it was fairly labor-intensive calculation to do it manually. And then we learned some shortcuts using our calculator with that binomial PDF, all right? So now what we're doing now is, and then after we left that, we've done a whole bunch of stuff the last 6-8 weeks on normal curves, right? The bell-shaped curve that you hear in probably in your science classes, standard normal curve, and that area under the curve, when we slap a scenario on there, we started that with using SATs and IQ scores, and we've done other things on there. Anything that's called standard or normal would apply to that standard normal curve, and that area under the curve exactly corresponds with probability. Those values in the area under that curve are the exact same values. It's one and the same. The area equals the probability. So that's kind of a summary of where we are and what we've done the last 12 weeks or so, maybe. So what we're doing in this last section of chapter 6 is we're taking a binomial situation and putting it into a standard normal curve situation. We talked about in the slides the other day that one of those is a continuous variable. Remember, that goes clear back to September, right? Continuous is a variable that you measure with an instrument, speedometer, stopwatch, yardstick, yardage on the football field, whatever it is, right? Versus discrete, which is the standard normal curve stuff. 6 of these, 8 of those, 10 of those, discrete we count, all right? So there's some kind of hocus pocus, smoke and mirrors stuff that has to occur or happen to do a binomial as a standard normal curve. Well, why are we doing that? Because you already told us how to do binomial. Well, the reason you're doing it is the standard normal curve, bell-shaped curve, has many practical applications and used in a wide variety of things. And the calculations are less labor intensive. So that's why we're doing it. So again, that's kind of background and history and kind of a review and recap. All right, so to do a binomial as a standard normal curve, there's a couple conditions that have to be met, right? Let's see if we can, I think it works better with the lights off. Let me turn the lights off.
Put me down.
It's all right. Somebody say something?
Oh.
There's administrative folks jumping around Zoom classes today, so you may want to take your hats and hoodies and things off, all right? But anyway, normal approximation, right? 2 things have to occur. We have to do a quote unquote test. N times P, what's N? N is the number of trials. What's P? The probability of success. Both of those are going to be provided to you. You don't have to create those numbers out of thin air. They're going to be provided to you in a scenario. Has to be greater than or equal to 5. then n times q has to be greater than or equal to 5 for it to be practical. And today we're going to do some binomial situations. A standard normal curve, the normal approximation. It's an approximation because it's not exact, it's not precise, but to get it fairly exact and fairly precise, you have to, this test has to apply. Otherwise, it doesn't work well. The values aren't going to be very precise and good for you. All right. So if it's not, what can we do? What can we manipulate to make it work? And that's kind of what you did in that problem set on Monday and since then. The only thing you can manipulate is what? In terms of those series of 3 graphs, and there was like 3 different series of 3 graphs that we talked about in the slides on Monday. What were they manipulating to get those graphs to look like to kind of morph or transform from something that didn't look like much to morph or transform into a standard normal curve? What were they manipulating? Which variable?
N, number of trials.
Yeah, you can't change P and Q. P and Q, it is what it is. All right. So the only thing you can manipulate is N. All right. And that N, if you remember, don't, but if you remember, if P is 0.5, then Q is 0.5, right? Because P and Q added together always have to equal 1. And if you kind of remember, kind of analyze those graphs a little bit, you may want to do so after class, either looking at the PowerPoint presentation or your textbook. As you get further, as P gets, or and Q gets further from 0.5, because like if P now goes from 0.5 to 0.3, then Q now goes from 0.5 to 0.7, because again, they're kind of complementary events. Everything under that curve has to equal 1. The issue that occurs, and if you remember, not to pull those graphs back up, but you may want to look at them when you're doing this problem set. If P and Q get further from 0.5, then N has to get bigger and bigger for this N times P and N times Q equal to be greater than or equal to 5. All right. And if you noticed, like a couple of those were on the graphs, I think it would have like P as 0.1 or 0.2. Well, you had to get up to like 50 to 100 trials to get that curve to morph into a standard normal curve. All right. So what you had to do on those bottom 3 calculations on that problem set 1 is there was 3 scenarios in that previous 6. I think it was 3. Yeah, it was 3 where N times P and N times Q did not equal 5, or was not greater than or equal to 5. So remember, the formula is N times P is greater than or equal to 5. To find out what do I have to raise that N to make this be able to be used as a normal approximation of a standard normal curve, is I just, thinking back to your Algebra 1, Algebra 2 days, I'm just going to try to calculate that new N. So it's going to be N is greater than or equal to 5 over P. And that's how you did, let me just grab my sheet from the other day. That's how you should have solved those 3 bottom boxes on this thing right here. All right. I'm sorry, some of your guys, when you sent those things back into me, the boxes all morphed from what I gave you. So again, I talked with the tech guy. I'll start sending you, instead of sending these as a Word document, I'm going to send them as a PDF, and that may keep these boxes from, again, something else that's morphing. But if you want to look at your sheet there, that number one on that sheet did not meet the requirement, because if you remember, number 1, right? Number 1, the N times P equaled 2, and the N times Q equaled 48. Correct? It was 50 times 0.04. and it was 50 times 0.96, right? So we figure out, well, what n do I need? You can see that, what n do I need to make that scenario be able to do a normal approximation? So what you had to do is you had to go using this formula of n is greater than or equal to 5p. So p in this situation was 0.04. So we go n is greater than or equal to 5 over 0.04. Believe, right? Yeah. And 5 divided by 0.04 means comes out to 125. So we had to have a sample size of 125 in that problem set number one, that problem number one on problem set one to actually work. Does that make sense? Questions or confusion? All right, let's see, number 3 was also a no. Just to kind of bring you up to speed on number 3. Number 3, the probability of success was 0.3. So again, using the same formula of n times p has to be greater than or equal to 5. So n has to be greater than or equal to 5 over p. So in number 3, if we put 5 over, I think it was 0.3, wasn't it? Yeah, 0.3. It came out to like 16.77. Well, you can't have 16.77 trials, right? So your answer should have been 17. Make sense? Questions, confusion? And then number 4 was also a no, and you should have come up with an n of 1,000, an n of 1,000. Any questions? Any confusion? Everybody else did fine on the previous 6. It was just there was some mess ups on what's the new n value have to be for this binomial situation to be able to apply it to a normal approximation or to the normal standard curve. All right? Any questions? Any confusion and clear up? Because we're gonna up the complexity intensity here from here and do some actual scenarios. Are we good? Before we jump into it head first. All right, here we go. Hearing none. All right. Let's see here. Okay, so in Blackbaud in the assignments, there's a problem. The problem set I'm going to go over is there. If you're set up so where you could print it out, that's great. But if not, just write down the problem number. I'm going to give you the basics. I'm going to walk you through number 1, okay? And I'm going to get you started on number 2, and I'm going to give you a couple watch out fors, be careful ofs on a couple of the other problems. So make sure that they're done correctly, okay? All right, let me get this lined up so you can see what you're doing. And I'm going to go back just to enlarge it just a little bit. All right, so here's the scenario. All right, it says, determine the normal approximation. It's a binomial probability, all right, for when x equals 6. So that's our x value, all right. N equals 12, and n is what? N is the number of
Trials.
number of samples or number of trials, and our p equals 0.6. So that's pretty close to 0.5, so hopefully we won't need that many trials. So and the steps I'm going to walk you through work on all 5 or 6, all these problems in this problem set. The mechanics, the process, the flow chart, the methodology is the same for all of these. All right, so if p equals 0.6, what's q going to equal?
0.94.
0.94?
You're,
It'd be 1 minus 0.6, right?
yeah. Is it 0.06 or 0.6?
It's 0.6. It's
Oh, 0.4.
So
Yeah.
Q is going to equal 0.4. All right. So and stop, ask me a question or stop me if you get lost in the process. Again, I would write this down because this is kind of the recipe flow chart of how to solve this. So we know if P is 0.6, Q is 0.4. All right, so the next thing we're going to do is calculate N times P and N times Q, just like we did in that problem set on Monday, and see if they both are greater than or equal to 5. So if we do that, we've got 12 times 0.6, which equals 7.2, I believe. Let me just double check my math, doing this from memory. All right, so that's checked. That works good there. And then we got 12 times, it was 0.6, times 0.4, which equals 4.8. All right, and it's close to 5, but it's not greater than or equal to 5. If you always look, the products of N times P and N times Q, or the sum of N times P and N times Q, is always going to equal the number of trials. If not, you've run into a problem. Okay? So for the sake of argument, normally you'd stop right there. This doesn't meet the test, so I can't do it. I'm going to throw it out. I'm going to move on and do something else. But for the sake of argument, we're going to do it. All right? And we're going to compare this value using standard normal curve versus your calculator and see how close they are, all right? And we just talked about it over there, all right, Ed, a couple minutes ago. And since it doesn't meet the value, it's not going to be as close as what it could or should be. But we're going to go through the steps anyway. This would have to be 5 or greater for this to work. But we're going to work through this. We're going to work through it anyway, and we'll come back and address this again at the end. Everybody good so far? Roy, you all right? Let me do something here. I'm going to change something.
How are you doing, sir? It's the real question.
Hey,
Hanging in there, I like to get back to normal sometimes.
everybody does.
Let me. All right, let me.
Sir, quick question.
Yes, sir. Fire
Sir,
away.
virtual online is so hard.
Let me get Mr. Gore's question.
No, Daughtry can go first.
I was just saying this stuff is hard.
Hard?
Online learning.
Well, I mean, it's hard. It's harder for you all because I can't see your body language. Your body language cues like, yeah, I'm getting an or not. I can't look over your shoulder to point out maybe where things are breaking down or messing up. It's just it's harder for us to instruct. It's harder for you to gather the information and retain it. But it's better than not doing anything. And that's one of the good things I can say. It's at least we're trying to keep some instruction going. So we can't sit around you can't take a 5-month break from education and come back in late August and be ready to go. I mean, that's a long lapse.
Public schools are doing.
Yeah, and just look how much sharper and brighter and more intellectually advanced you will be. Ba-dum-bum. All right, here we go. Okay, everybody good so far? Okay, so it doesn't meet the 5, but we're gonna address this. We're gonna do this just for the sake of argument, and that way we're also gonna compare this value versus what it would be on your calculator. All right, so what's this little kind of funny looking U? What's that represent? That's the variable for what?
Mean.
The mean? Okay.
No. Is it?
By that. So the mean is actually N times P, right? So the mean
Yes.
is 0.2. The mean is always going to be the number of trials times the number of successes. And if you remember those graphs, that mean, that biggest bar on those 3 series of 3 graphs we looked at on Monday, they're also in your textbook, is always going to be N times P. So make sure you know that. You'll need to know that for the quiz and the test. But what else do we need for calculating Z-scores? That funny looking pig's tail thing. or 6? What was it, Mr. Bell? I can't remember. What's that symbol? We see that?
And deviation.
Standard deviation, all right? And if you remember, we've done 100, not 100, but dozens of these. That was N times P times Q under the radical, right? So in this case, it's going to be 12 times 0.6 times 0.4 under the radical. And I'm going to just kind of expedite the math. That equals 1.7. So our standard deviation is 1.7, our mean is 7.2. All right, so any confusion before I kind of move on? Let's draw, let me do a graph and then we'll talk about it. So here's the graph. Let's see if we can see that. Just go up a little bit, yeah. All right, here's the mean of 7.2 we just determined in my nice, neat, accurate graph. And it's asking you, what's the probability of x equals 6? Okay. Does the term continuity factor ring a bell to anybody? All right, we talked about it on Monday, all right? Continuity factor doesn't make sense. I call it really a correction factor, but I'm going to use what the textbook says. So what's this thing? What are we asked to solve? The probability of x equals 6. Remember, this whole area under the curve equals 1, all right? And it's asking us for x equals 6, which is a single bar here, right? Well, how do you measure that area? Remember the purple and the light blue graphs? That continuity factor is 0.5. So what we're really going to determine now is we're going to go, it's not to scale. So we're really going to use, instead of 6, we're going to use 5.5. I know this is little, to 6.5.
Sir, could you move your camera a little left?
This way?
Yep.
The other way.
Yeah, that's perfect.
Okay. So really we're gonna measure now, because 6 is just a vertical line. How do you measure that area? This is that continuity factor we briefly talked about on Friday. So we're actually gonna determine this area here. I know it's not to scale. So for between 5.5 and 6.5. All right. I think a correction factor is more of a thing. There's a more accurate name for that. So we're not going to calculate 2 z-scores because we've got a kind of a designated area to calculate. So I've got 2 z's here. I'm going to do them kind of simultaneously. So now my x is 6.5 minus the mean of 7.2 over the standard deviation of 1.7. I put the larger one on top. I'll explain that in a minute because it makes the math easier. And then I also got to do the same thing for 5.5. All right, that's just the standard z-score. X minus the mean over standard deviation. All right, good. Anybody lost? Everybody good? Can you see it okay? Come in closer.
Yep.
So if we do the math, remember it's always x minus the mean over standard deviation for both of these, it's going to give us a z-score, which in
Wait,
this,
what does that say? 6.5?
yeah, because remember that continuity factor? So it's a half above it and a half below it. So for 6, we're measuring that again because we're measuring area, which equates to probability. It's 5.5 to 6.5.
And then 1.7.
All right, and then if we do the math, this value equals negative 0.41. If someone's checked behind me, that's fine. And the other one equals negative 1, all right? So if we put z-scores with this, 6.5 is negative 0.41, and 5.5 is negative 1. Because we know the z-score at the mean is 0, and it goes down to negative about 3.5 to the left, and it goes to a positive 3.5 to the right. All right, so now we got 2 z-scores. Everybody good? Anybody lost? All right. And my formerly nicotine stained fingers is table 3. It's also in the back of your textbook. All right, remember this guy? Hopefully you've got that there handy. All right, and we read down the z-scores down the left column for the tenths, and then we come across for the hundredths across the top margin, right? So to get the corresponding areas for those two z-scores we just calculated, I'm going to slide down a little bit. Okay. All right, let's see, for negative 1, that is 0.3409, all right? And for negative 1, 587. All right, hopefully I don't have to compete with your music. All right, so let's to refresh our memory, this 3409 is this 6.5 going this way, right? 0.3409. And this 0.1587 is from that 5.5 point this way. This area right here. That makes more sense. So I'm going to subtract this 1587. I'm going to subtract this 1587 from 3409. That's why I stacked it the way I did with that larger X on the top.
Mr. Gaffney.
It's all lined up. Everybody having fun? Let's see, I'm trying to make sure you can see it. So if I subtract the 1587 from 3409, this will give us this little shaded area in the graph, which in this case equals 0.1822. Just double check my math. 0.1822. Okay, so another way to look at that makes maybe more sense is that's 18.22% is the probability or that area between 5.5 and 6.5. Does that make sense or any confusion? I mean, we've done, lots and lots of these, so it's nothing new other than we're taking a binomial and kind of webbing it into a standard normal curve calculation. Questions? Before we move on. Okay. Anybody got their TI handy?
No.
Yes.
Mr. Gore says he does. Okay, so hit the, on your TI, hit that second key and that distribute key. Okay, DISTR, I think is on there. All right, second derivative.
Where's the distribute key?
It's over there.
Oh, I got it.
All right, and then slew down till you get to binomial PDF. PDF.
Okay.
Hey, Mr. Doctor, is that you having fun with my name?
No, sir, that's not me.
Mr. Gore, you got the PDF? Now come down to PDF and type in N for 12, P is 0.6 and X equals 6, and then hit enter, I think, twice. And tell me what you come up with.
0.1766.
All right.
17657.
All right, so 0.1765, is that what you said?
Mm-hmm.
All right, so for the TI, you got 0.1765, all right, versus the 0.1822. Let's see if we can see that. Yeah. All right, so it's within what? A tenth. No, actually within 1/100, so it's fairly close. It's fairly close. That, and what you just did with your calculator, that was, remember that old binomial coefficient? You would have had 12 over 6 times what? 6 to the 0.6 and 6 to the 0.4. All those calculations you would have had it done manually. So it is, even though I kind of walked and kind of belabored some points, you could, if we did this without all the explanation, you could do this in 3 or 4 minutes, as opposed to maybe 8 or 10 minutes of using that old binomial calculation. Now, this would have been a whole heck of a lot closer, if that N times Q value was greater than 5, all right? But it's still fairly close. We were close to 5. And that's why they have that test. The N times P and N times Q has to be greater than or equal to 5 for this to give you a more precise value. Any questions? Any confusion? James, you all right?
Yeah.
Guys, you're not supposed to be wearing the hoodies. All right. Okay, so we got 10 minutes. All right.
I'm still gonna wear my hoodie.
Now, on the problem set, be careful, all right? And number two, I'm going to kind of set you up for number two. Any questions before I'm going to kind of get you at least started on number two. I don't want to keep going. I don't want to keep going. I'm going to erase this because I'm going to use the exact same recipe I just used to solve this, all right? You good? Okay, so let's see. We're going to change things up on you. All right, I'm going to use black just to mix things up. All right, this is problem set number 2 on the problem set. So if you want to just do everything on loose leaf paper when you put it in Dropbox between now and Friday, that's fine. If you want to transfer it over to the actual problem set. So in problem set number 2, let me just come back a little bit so you can see everything. All right. I'm going to give you a caveat, which I spelled out on the problem set, all right, that you got to watch out for. All right, it says, number 2 says, determine the normal approximation.
Jeff, go easy on me.
Bruh. Who did that?
How come Mr. James and Mr. Daughtry's screen comes up when those things?
So did you just say Mr. James and Mr. Daughtry?
Yeah.
Wow.
'Cause whoever's talking, wherever the noise
Whoa,
comes
Lord.
from, their screen lights up on my screen. So it's not hard to figure out where the noise is.
It's because we're not on mute.
Ah,
Yeah.
all right.
I'm staying on mute the rest of this thing. I'm not getting.
All right. Better safe than sorry. All right. But just make sure you have your camera on. Otherwise, I got to kick you out. All right. So it says determine the normal approximation of the binomial probability. The probability of x is less than or equal to 8. Probability that x is less than or equal to 8. All right. Let's see. Where n equals 14. It's a nice solid number. And p equals 0.4. All right, so that's the scenario. All right, pretty good. Now, the reason I erased that is because, again, the mechanics, the methodology, the flow of this is exactly the same. The only thing that's changed is the values. You ready? All right, here we go. So if p is 0.4, q equals what? This is participatory learning.
0.6.
0.6, there we go. So n times p is 14 times 0.4, right? And q is 14 times 0.6, right? I'm gonna give you a minute to do those. Mr. James, it says your bandwidth is low. I hate it when you have low bandwidth. All right, so what's 14 times 0.4?
5.6.
There we go. 5.6. What's 14 times 0.6?
8.4.
8.4. Gore's on top of it. If you don't have to do this, but if I add these together, they better add up to 14, right? All right. So what's my mean of this scenario? You've already calculated it. What's my mean? You just did it a minute ago.
5.6.
It's 5.6. You may want to make a note. The mean's always n times p. All right. And then the standard deviation is the n times p times q under the radical. I'll do that one for you, which comes out to 1.83. So all that's exactly the same. Now here's the kind of watch out for, be careful of, okay? I'll leave that there. I'm going to draw a picture of what we're actually calculating, all right? Now that we know what the mean is. Let's see, we said the mean was 5.6. Now, this says we're calculating the probability of x is less than or equal to 8. So I'm just going to kind of Yes, so we're going to determine this area. All right. Now, remember the continuity slant correction factor. What is the continuity slant correction factor? What's the value? You got to know this. Equals 0.5, all right? So we're actually, and that's one of the quirks to this normal approximation of a binomial. So we're actually going to use, we're going to go opposite of whatever they're asking. Remember on the 6 over there initially, we went 5.5 and 6.5 because it was a single probability of x equals something. When it says x is greater than or something or less than something, you go opposite the direction of whatever it's asking. So in this case, we're actually going to, our x is, because of that correction factor, is going to be 8.5, not 8. If it asked for greater than 8, we would have used 7.5. And that's the part that's going to mess you up. If you don't remember that, you got to, I don't have any tricks or whatever to remember that, but it's that's that continuity correction factor. So we're asking for less than 8, less than or equal to 8. So we go opposite, it's 8.5. If this problem, one more time, it asked you for greater than 8, instead of 8.5, we would have used 7.5. All right? Don't forget that. I can't just make a star or note, whatever. Continuity factor, so I like correction factor. All right, so we only have to calculate one z-score with this, right? So now we go z, we got everything we need to do that. We got z equals 8.5, our x, our new x with the correction factor, minus the mean, which we said was 5.6, over our standard deviation, which was 1.83. Everybody see that okay? All right. So if we do that math, it comes out to 1.58 z-score. Is that right? Let me double check my math. 1.58. Right? So this would have, because the z-score for 5.0 is 0, the z-score for 8.5 would have to be 1.58. That all makes sense, right? We've done a lot of this. All right. So now we go to a handy dandy table. And we look up 1.58 and we get 0.9429. All right, so it's saying that the probability of x is less than or equal to 8 is equal to, let's simplify things, 94.2%. Okay. I know Mr. Gore's got his calculator there. So since he's handy dandy with it, now, Mr. Gore, take your calculator, hit the second key, the distributive key, and scroll down. Caution. Before we used binomial. I made a note. Use binomial PDF, and let's see, how was that formatted? Looks like that, all right? The P stands for a specific value, like we did, what was it? Was it 6 in the first problem? Yeah, 6, all right? That's just giving you that one single value. In this case, we're going to use binomial CDF, all right? The reason we're using the C, can we see that? Let's come down just a little bit. The C stands for cumulative, all right? Because if I just did 8, it would just give me the probability for 8 using that calculation with the binomials. We're kind of relating back to binomials, all right? It's just going to give me for 8, but the question is for everything less than or equal to 8. So that's, if it was just 8, and that's why I use the 6 and the PDF in the first problem, and this one we're using cumulative because it's asking you for 0, 1, 2, 3, 4, 5, 6, 7, 8. And if you did this as a binomial calculation, you would have had to done 9 calculations and added them together. if we did it the old-fashioned manual way. So now, Mr. Gore, if you would hit the binomial, come down to binomial CDF, not PDF, and then use n as 14, x as 8, and p as 0.4. Tell me what you come up with.
X is 8, right?
X is 8.
Oh, hold on. Binomial CDF.
Yes.
Oh, there we go. Oh, there we go. All right. Trials 16 is 14. P 0.4 X 8.
8.
0.941.
0.941.
Mm-hmm.
If you look, these are almost identical. Pretty darn close. Am I down low enough? 0.941 versus 0.9429. So it's tenths, hundreds. It's within. I mean, if we just do it to hundreds, it's identical. It's at the thousandth mark where we start to differentiate a little bit. And you can see this is a lot closer than that other one because that first number, problem number 1, remember, we didn't quite meet that n times p and n times q calculation of greater than or equal to 5. All right, so that got you through 1 and 2. So you just have 3, 4, and 5. 5's got 2 parts to it. So you got 4 problems to do. Drop them in Dropbox on by Friday afternoon, Friday evening, so I can look at them before Monday morning. And then Monday, I'm going to wrap up any loose ends on chapter 6 and particularly the second half of chapter 6 and give you a quiz that day. A couple of just caveats, watch out for us. Remember that continuity correction factor. If it's asking you less than or to the left, go to the right. If it's asking you greater than or more than, let's say it was 8, go to the left, go the opposite direction and add or subtract that 0.5. Right? If we had subtracted 0.5, we would have lost 7.5 to 8 as part of the calculation. So that should have been a red flag. It doesn't work. If it's a single value, such as a 6 in number 1, or let's just say 9 for the sake of argument, if it's 9, you're going to use 8.5 to 9.5. It kind of explains that back in those slides, probably in the slides 7, 8, 9, 10. I can't remember it in the PowerPoint from the other day. So last problem set for this section, unless you want, I've got more, but I think this will be enough to kind of get you semi-proficient in doing normal approximation of a binomial. Anything I can clear up before I cut you loose?
Nope. Thank you, sir.
Everybody have a good weekend. I've got office hours from 2 to 2:30, and except on Friday, it's 9 to 10. So if you run into a snag or a problem or want some extra help or a question, or you want to pick up 10 points on your etiquette participation grade, check in with me during office hours, even if you just want to say duty. All right. Any questions? All right, we've exceeded our time limit. So you got your money's worth. We will see you next Monday, if not before. Bye-bye.